Hello everyone, welcome to the Spectral Geometry and the Clouds seminar. Let me remind everyone that the talk is recorded, and let me welcome the speaker of today, Javier Serrano. He will speak about computer-assisted proofs and counterexamples in spectral geometry. The floor is yours, Javier.
Thank you. Thanks a lot, Alexandre, for the invitation. And thanks everybody for for coming today to the talk. So first of all, a small disclaimer: I'm kind of new to this area, so I apologize in advance if I miss citing somebody or if I make mistakes of that sort. And thanks a lot for inviting me to this talk. So I'm going to talk today about two papers written. The first one written with Gerard Oriols, who did his senior thesis under my supervision at Princeton, and now is a graduate student at ETH. And the second one with Joel Dane, who is my graduate student at Uppsala University and who is also in the audience, and Kimberly Ho, who is currently a sophomore in the math department at Princeton. Okay. Oops. Okay, so let me summarize the main takeaway message of this talk. So I'm going to explain a new method, or at least a method that I hadn't seen before in this context, which is going to allow me to construct solutions, or at least small perturbations of solutions. And this method is going to be constructive. So I'm going to be able to have quantitative information of the solution, and I will try to exploit that to my advantage. The ideas are quite simple. They are not very, very deep. So the ideas are very easy to be understood. And this is a method that is going to be suited towards finding some solutions. And in particular, it's going to be suited towards finding counterexamples with open conditions. And I will be more precise about what I mean by open conditions. This method involves a computer-assisted proof. And I will also be more specific about that. And throughout the talk, all of my boundary conditions are going to be Dirichlet, but the method really doesn't care whether they are Dirichlet, Neumann, or even Steklov. Okay, so I'm going to present this method by means of these two examples on these two papers. Okay, so first of all, what do I mean by a computer-assisted proof in this context? So in this context, what I mean by a computer-assisted proof is the following. So we start with a problem, with our favorite problem, which is infinite dimensional, and it's typically infeasible by hand. Let's say finding some solutions or finding some counterexamples of a certain equation. And then we're going to do some pen and paper reduction that will reduce the problem to a finite set of calculations, which are typically going to be open conditions. And what I mean by these open conditions are pretty much inequalities. Okay, so I'm going to reduce the infinite dimensional problem into a huge set of inequalities, and that if I'm able to check, then I can prove whatever I had in mind. Okay, and this checking is what the computer is going to do. So we will carry over all the errors and everything that the computer may make, and we'll and we'll treat those things as an error, and then we will check that in fact those inequalities are satisfied. And this is why we need an open condition versus a closed condition. So we will be able to take care of all the errors if we have a little room on the estimates that we want to prove. Okay, and just to be clear, this is not numerical simulation, and everything is fully rigorous. We will use interval arithmetics whenever we need them, and in fact, we will need them very often. Okay, and the end result is a fully rigorous mathematical theorem. Okay, so this is what I mean by a computer-assisted proof in this context. Okay, so let me start by talking about the first paper, which is not any three eigenvalues determine a triangle. So in this first paper, I will glance over the methods. I will not explain them in full detail, but I will sort of explain what is the idea behind them. And then in the second part, I will be more specific as regarding the methods. Okay, so as I mentioned, this is joint work with Gerard Oriols. This is his senior thesis, and he got a bunch of prizes for this work. Okay, so let me start with the Laplace equation, which in this context doesn't need any introduction. So we take a domain here, n is going to be, for this talk, is going to be 2 from now on. And then one of the most famous questions is whether one can hear the shape of a drum, or in other words, if one can find two non-isometric domains such that the eigenvalues are the same. Okay, so the answer is no. And this is the most famous counterexample, but there are few results on the positive direction. Okay, so there are a bunch of results on the negative side, on the negative direction, meaning that the answer is no, but there are few on the positive side. Okay, so just to mention a few of them, Seldich proved that if under some reflection symmetry, if the domain is analytic, then there is a spectral determination. And then there are a bunch of papers by Hesari and Seldich lately where they have managed to prove that ellipses of small eccentricity can be heard. And also there is a recent preprint saying, proving that centrally symmetric analytic plane domains can also be heard. Okay, so how about this problem in the polygonal setting? Well, D'Urso, in her thesis, using wave trace arguments, proved that if you have two triangles and they are isospectral, then they have to be isometric. And this this proof, Grise and Marona gave a different proof using heat trace asymptotics and exploiting the terms that one gets using the heat trace asymptotics. So triangles are determined in the class of triangles. And lately, in a series of papers, Hesari, Lu, and Rowlett have proved that trapezoids under certain conditions are isometric in the class of trapezoids. Together with Alberto Enciso, we showed that if you take a regular polygon, but you don't constrain to the number of sides, then you can hear any regular polygon in the class of polygons. And in fact, we prove a statement which is more general, which is that you can hear what we call semi-regular polygons, but I will not talk about this today. Now, what's the problem? Or where do I see the problem? The problem is that from this point on, we are trying to classify, or we are trying to hear domains on a space which is finite dimensional. And we are using the whole spectrum, which is essentially an infinite amount of numbers. So it seems that this problem is hugely overdetermined. So we have a lot of information, much more than what we should need in principle, right? So we have a finite dimensional space, and then we are sort of classifying solutions and understanding solutions using an infinite amount of numbers. So can we do it using a finite amount of numbers? So I tend to think of this as if before we had perfect pitch, now we are human and we don't have perfect pitch, so we can only hear well enough the first eigenvalues, and then from some point on we just can't hear them very well. So let's think about the easiest case, which is when drum is triangular. What can we say? Well, let's see. Can we do it with a finite amount of eigenvalues? So Chang and the Turk, using a contradiction argument, proved that for a given triangle, if you look at λ1 and λ2, and then a finite amount of further eigenvalues that depend on the triangle, then you can sort of hear it and distinguish it from the rest. But there are no estimates on how does this number of additional eigenvalues that you have to hear depend on the triangle itself, okay? Because it's a contradiction argument. So, okay, so this is kind of a suggestion that maybe a finite amount is enough. So if we count dimensions, and if we look at the dimension of this moduli space of triangles, modding out all isometries, then we have 3. So then the dimension of our space modulo all the isometries is 3. So it would be natural to conceive that the amount of eigenvalues that we need is 3, because the dimension of the space is 3. So Antunes and Freitas, about 10 years ago, did some numerics. And in the numerics, they saw that if one looked at lambda 1, lambda 2, and lambda 3, then it seemed that those 3 numbers determine uniquely the triangle. However, if one looked at lambda 1, lambda 2, and lambda 4, which are still another set of 3 numbers, then that was not true anymore. So then one could find examples for which numerically there were 2 triangles that share the eigenvalues 1, 2, and 4. And they tried with other combinations, and with all the others that they tried, they couldn't hear them. So they were finding 2 triangles that share those sets of eigenvalues, which were not the first, the second, and the third. Okay, and since then, no progress in this direction. Okay, so with Gerard, this is exactly what we proved. We found, or we can prove, the existence of 2 triangles, TA and TB, that look more or less like the ones that I drew, so they are not close to each other, for which the first, the second, and the fourth eigenvalues are going to be the same. Okay, and these are small perturbations of the ones that I drew here. Okay, so let me set up the problem. So first of all, because I have all this freedom with the isometries, then I can fix one side to be 1 and put it so that, and this is going to be the longest side, so that one coordinate is at 0, 0, the other one is at 1, 0, and then what determines my triangle is going to be the third vertex, which is going to be x1 and x2. Okay, so my space of triangles is going to be indexed by x1 and x2, and I'm going to look at the quotients of the eigenvalues. Then rescaling, I could make all 3 eigenvalues to be the same. So essentially now what I have is a function xi to 1 and a function xi for 1 in a space, in a 2-dimensional space. So I want to find 2 points in my space for which the functions xi to 1 and xi for 1 are equal, both of them. Okay, so numerically, this is what I wrote. Numerically, find 2 candidates, T1 and T2, which are identified with these points x1, x2, such that both functions agree on these candidates, or at least numerically, they are very close. So this is a picture taken from the paper by Antunes and Freitas. And on the left, we see the level sets of xi21 and xi31, which is lambda 3 over lambda 1. And on the right, we see xi21 and xi41. So on the left, it looks like as if these 2 functions determine uniquely the point. So there are no 2 points, no 2 different points for which the two functions agree. There seems to be some sort of monotonicity in terms of the level sets. Whereas on the right, the 2 depicted points share the same level sets. They lie on the same level set of xi for 1, which is 297, and then they are on whatever the level of the dotted curve is. Okay, so this is sort of our starting point, and this is where we saw that in fact there were these cases. And of course, this is an open condition. If one perturbs the dots a little bit, one can still find yet another solution. Okay, so this is sort of when we started working, and this is our domain, and this is the point where we actually look for solutions, which is different from the one that you saw before, basically because of technical reasons, because the conditions that we have to check are easier to be checked here. So now we have 2 points, A and B, which you can think of as being the same as the black dots before. But instead of proving that the 2 functions agree on A and B, this we cannot do because that's a closed condition. So instead, what we're going to do is that there exists a point inside the green parallelogram A for which the two functions are equal to some other point inside the parallelogram close to B. Okay, so we don't know exactly what is that point going to be, but we know that we can pick one inside each of the two parallelograms for which this condition is going to hold. Okay, and we're going to use the Poincare Miranda theorem that essentially says that if we have two functions and one, let's call them f and g, and f is positive here, f is negative here, g is positive here, and g is negative here, then somewhere in the middle of the square or the parallelogram, there is a common zero of f and g. Okay, so this is the soft analysis that we're going to use. And now, because of this, we have transformed our problem into finding a sign of this function, which is going to be c to 1 minus c to 1 bar, which is this fixed value, and c for 1 minus c for 1 bar, which is this other value, on the sides of this parallelogram. So now we have transformed the closed condition into an open condition that has to be checked along all four sides of the two parallelograms. Okay, so we have to check this sort of condition in the four sides of the two parallelograms. Okay, so this is good news because now we have an open condition. Okay, so but still this is unpleasant because this is an infinite amount of triangles. So this is still needs to be massaged a little bit. Okay, so let's see how we can do it. Now let's think about how we can provide eigenvalue bounds. So essentially here there are sort of two lines of thoughts. One is to use finite element methods, and both sort of have their own advantages and disadvantages. So if we use finite element methods, this is good in the sense that we will, along with the eigenvalue, we will also get the position of the eigenvalue in the spectrum. The drawback of this method is that the lower bounds that we can prove using finite element methods are typically not very good in the as compared to the other methods. So these lower bounds for our problem are not good enough unless we use a mesh which is ridiculously small, and then it will take forever. So this is out of the current software and hardware requirements. And then on the other side, there is the method of particular solutions, which has very good precision. There is a typo here. This is not exponential, but root exponential. Using what is called now the lightning method, which was coined by Gopal and Trefethen 2 years ago. And I will say a few more words about this later on. And the drawback of this method is that given that it is much better in terms of precision, it doesn't tell you what position does this eigenvalue occupy in the spectrum. So it just tells you, okay, in this small interval, you have an eigenvalue, but you won't know whether this is the first, the third, the fourth, and whatnot. Okay, so what we decided was to do two passes and use the advantages of each of these methods in each of the passes. Okay, so we're going to do a combination of both families. In the first pass, what we're going to do is to decouple the fifth or the fourth eigenvalue from the rest. So we will just provide a lower bound on the fifth eigenvalue, and then, which is not too good. Okay, so this is the sort of thing that we are going to split in our first pass. And then in the second pass, we're going to find 4 eigenvalues, which by the bound that we had before, have to be the first 4. Okay, and now the enclosures around these 4 eigenvalues are going to be very, very tiny because we're going to use the power of the MPS. Okay, so this is how we're going to proceed in order to find very small enclosures of the first 4 eigenvalues. Okay, so in order to find the tight enclosures and the small enclosures, we're going to also use stability results by Barnett and Hassel using quasi-orthogonality arguments. Okay, so this is the plan. Okay, what can we do using finite elements? So there is a theorem by Liu where he proves that if one can bound the discrete eigenvalue, lambda hk, h is the size of the mesh, and k is the position on the spectrum, coming from the discretization using finite element methods, then this implies some lower bound on the true eigenvalue lambda k. So lambda k, this is the discrete one, and this is, let's say, the continuous one. Okay, so we can lower bound the continuous, the eigenvalue of the Laplacian by means of a bound on the discretization of the Laplacian. Okay, and these scales like this, C is universal, and we can get these bounds, which for the fifth are good enough. So now, if we manage to do so, then we win. And in order to do so, we need to solve now a linear algebra problem, because now after the discretization, this becomes just a linear algebra problem with a very big matrix. Okay, so we have to bound rigorously the eigenvalues of a big matrix, but this is a lot easier than what we had a priori, which was to bound just a spectrum of an infinite dimensional operator. Okay, moreover, our matrix is going to be symmetric, so this is good news. And what we will do is to find an approximate diagonalization, an approximate orthonormal basis, and prove that close to our approximate orthonormal basis, there is a true orthonormal basis nearby, with estimates on the error between one and the other. And then once we do that, then the true eigenvalues are going to be preconditioned by the approximate eigenbasis, and then the true eigenvalues are going to be very close to the eigenvalues of the precondition matrix. Okay, with explicit bounds on the errors that we make at each step, so that then we're going to get an approximate diagonal matrix, and we can take out all the errors, sweep them under the rug using Gascoigne's theorem. Okay, so this is how we are going to proceed, and then the job is done. Okay, so this is sort of how it works. So having done that, we can and then we can produce enclosures of the first, second, third, and fourth, and that is enough to get the bounds that we wanted on one point on the side. Okay, so this would, up to here, what this would produce would be, let's say, on our parallelogram, let's say a bound on a certain point, one particular point. So in order to grow this point to do the full side, we use monotonicity arguments. Since the result, since the condition is open, we have some spare room, and we can grow a little bit our dot, so that now we can go up to a certain region here in parameter space. And then once we finish, once we cannot grow more, then we check the next point, we grow, and we check the next point, and so on. And by doing that, we don't need too many triangles on each of the sides, and we can continue doing that until we hit the end of the parallelogram. We do this on all 8 sides, and we are done. Okay, so this is how the proof works. Okay, so this is roughly the plan for this theorem, and this is how the proof works. Now let me move on to part 2. So part 2 uses a similar philosophy, but for a different problem. Okay, so in part 2, I'm going to discuss the construction of counterexamples to Payne's conjecture, and we'll give some more details and some twists that we had to do for this particular case. So this started as a summer project for Kimberly, and then at the end of the summer we were not done, and it grew into a fall project, also bringing Joanne in. And we wrote a paper, and it's on archive, and we posted it like a couple of months ago. Okay, so let me start by recalling Payne's conjecture. So Payne's conjecture is easy to state. It just says that if you take a bounded domain on the plane and you look at the nodal line of the second Dirichlet eigenfunction, then it has to touch the boundary. Okay, and later Yao wrote a similar statement in the higher dimensional case. Okay, so there are some positive results where the conjecture is known to hold. So if the domain is convex under suitable assumptions on the smoothness of the domain, Melas and Alessandrini prove that, that the conjecture holds. And then under some symmetries or convexity assumptions, Payne, Lin, Puta, Damascelli, Young and Go, and many others have also managed to prove the conjecture on the positive direction. Okay, how about the negative? So on the negative direction, there is a counterexample, and this counterexample was found by Hoffman-Ostenhoff, and Nadirashvili in 1997, and later extended to higher D by Fournet and Kennedy. So the way Hoffman-Ostenhoff and Nadirashvili constructed this counterexample was to start with this domain, which is like two annular domains sort of separated by a hole, and then carve little connections between the two regions. And this is an asymptotic result. If you carve enough connections and send the number of connections to infinity, then you can get a domain for which the nodal line is going to be closed, and it will be sort of around here. Okay. And in some of these papers, there were some comments about the amount of holes that you have. And well, the more optimistic comments said 10 to the 9, and the less optimistic comments said an astronomical number. Okay, so in their paper, they also raised the question, what's the minimal number of holes that you can provide a counterexample with? Okay, so what's the smallest number of boundary components or of holes for a counterexample? And since then, as far as I'm aware, there were no results. So what we did is the kind of a first step in this direction, and this is the counterexample that we present. So we can construct a counterexample given by a planar domain, which we see on the left, that has six holes, so 7 boundary components, for which the nodal line of U2 does not touch the boundary. Okay, so in the left we see the domain, in the center we see the eigenfunction, and in the right we see sine of U log of U2, just to highlight the positive and the negative parts. And it looks as if it is touching, but in fact it is not, and we will prove it. Okay, so now let's see how we can prove that this thing actually has a closed nodal line. Okay, so the first thing to mention is that by no means our domain is special. We played around doing numerics, and we found many other domains with sort of different, maybe not different topologies, but definitely very different looking, at least to the eye. Okay, so all these 4 domains seem to have a closed nodal line, although the only one for which we prove it is for the last one. But we can see that putting the holes in one way or another does matter, but to a certain extent, because if you move the holes a little bit, then this property will be destroyed. But on the other hand, on a positive note, there seem to be many counterexamples for which this nodal line is closed and very different from each other. Okay, so now I'm going to be focusing just on this one. Okay, so here's how the construction is going to work, which is sort of in a similar spirit as before. We're going to find good numerical approximations of U2 and of lambda 2. We're going to find good bounds for this approximation, essentially proving that there is U2 is very close in a quantifiable way to U2 tilde, and lambda 2 is going to be very close in a quantifiable way to lambda 2 tilde, and we will certify the index of the approximation. So this is going to be similar to what I mentioned before of the work with Gerard, but also to the work of Joel Dane and Bruno Salvi, where they did similar methods for the case of spherical triangles. Okay, so this is how the proof is going to work. Okay, so the first thing is to say, well, a priori, we just need to look at lambda 2 and u2, but life is not so easy. So if we look here, this gap is very small. It's too small. So with our current methods of isolating one part of the spectrum, we cannot do it. We cannot do for such a small gap using the finite element methods that I described before. So instead of trying to isolate the second from the third and then looking for two approximate eigenfunctions, then we're going to isolate the fourth from the fifth. Okay, so this gap is much more amenable to the finite element methods, for which the bounds were not so good. Okay, so we're going to now try to split the fourth from the rest, and there is an additional inconvenience, which is that there seems to be a double eigenvalue here. So we'll see how to deal with that in a moment. Okay, so the plan is to work as before, separate the first four eigenvalues, lower bounding the fifth, and then isolate them. And we will see what to do with the double eigenvalue. Okay, so as before, we use the theorem of Liu, which is written in a slightly different way, but nonetheless, it's the same. So if we can bound the kth eigenvalue of the discretized problem, then we can bound the kth eigenvalue of the true problem. And there were follow-ups of these results by Liu and Oishi. Okay, so now we have transformed again the problem of bounding, lower bounding part of the spectrum by lower bounding an element of an eigenvalue of a big matrix. Okay, so we want a lower bound for lambda 5, and instead we can get away by finding a lower bound of lambda h5. Okay, so what does the matrix look like? Well, if we look at the weak formulation of this problem and we define the stiffness and the mass matrices, then essentially what we are left with is with a generalized eigenvalue problem. And B is diagonal by the type of mesh that we did and by the choice of our element. So B is diagonal. And then we can sort of work our way and transform this generalized eigenvalue problem into just a regular eigenvalue problem. So now we have to work with this M, which is big, and we have to find the fifth eigenvalue and find a lower bound of the fifth eigenvalue in order to isolate the fourth from the rest. Okay, so this is reasonably big, and the amount of precision that we need is moderate to high. Okay, so let's be more precise as to what I was mentioning before. So we're going to use the following lemma. Suppose that we have some vectors in Rm, which are almost orthonormal. So these v1, v2, ... vm are going to be the approximate eigenvalues. So these are going to play the role of the approximate orthonormal basis of M. Okay, so once we have this, and S, typically S is going to be very, very small, much smaller than 1 over M. Remember, M is like of the order of 6,000, and S is going to be of the order of 10 to the minus 16. Then we can find a true orthonormal basis close by. Okay, and after having done so, then we precondition by this approximate basis. So we have an almost diagonal matrix D tilde, which is following from the preconditioning by Q tilde, and this will have approximately the same eigenvalues as M. And what we do is we compare d tilde with d by means of this lemma. D is the object that we want. D tilde is the object that we compute, and they are very close. So we take care of all the errors using Gascoigne's theorem and taking all the non-diagonal entries of the difference to be just perturbative terms, and this works. Okay, so this gives us the level of precision that we need in order to find lower bound for the fifth eigenvalue. Okay, so this is a sketch of where we are at this point. We have lower bounded lambda 5. Okay, so here we are good. And now we want to find u1, u2, u3, and u4 tilde, and lambda 1, lambda 4 tilde. And okay, in the best case scenario, which was as in the previous paper, these things are isolated, and then we can get enclosures which are narrow enough so that they can separate one from each other. But in this case, we're not so lucky, and we still need to deal with the double eigenvalue. Okay, so we can separate lambda 1 from the rest, we can separate lambda 2 from the rest, but we cannot separate lambda 3 from lambda 4. So this I will also explain how to deal with it. Okay, so how to find u tilde, u1 tilde, u2 tilde, and so on. So remember, the point is that this enclosure, I mean, this is not drawn to scale, but this thing is actually very narrow, and this is bad. So this is really a technical problem here. There are two constraints, and I will get into where is the second one coming from. But in reality, we need to provide a very thin enclosure of lambda 2. So this is something that we have to work hard to get. And for that, we need a very precise u2 tilde and lambda 2 tilde. So I'm going to explain what is behind it. And we're going to use the MPS method. So this was introduced by Fox, Henry C. and Moller, and it didn't take off until sort of recently, where it was revived by Bethke and Trefethen, and other people have been using this method as well. And now with the emergence of the Lightning method, then there are more papers and more research in this area. So the moral of this story is that we're going to construct solutions that fully satisfy the eigenvalue problem for a lambda tilde that is part of the problem, and we have to figure out, and they may not satisfy the boundary conditions. Okay, so we're going to postulate that our solution u tilde is going to be some big, so this n is typically big, linear combination of eigenvalues of eigenfunctions of this problem with eigenvalue lambda tilde, with no restriction on the boundary conditions, with no restriction on the boundary values. So we figure out the C case in such a way that this condition here is satisfied, or is satisfied in as much as we can. We try to select the C's in such a way that the value of u tilde on the boundary is minimized. Okay, and we pick the P's in a way that they satisfy exactly the eigenvalue problem. Okay, so examples, typical examples of P's that we pick are products of Bessel functions and trigonometric functions. And here you see sines, but they could very well be cosines. So this is a sort of basis functions that we're going to pick just to get the linear combination of u tilde. Okay, so we do that. We select a bunch of points on the boundary, and we try to minimize the value of u without getting the zero solution. Okay, so the zero solution is a solution of this problem, but of course it is useless for our purposes, and we want to get a non-trivial solution. Okay, so as I mentioned before, this method has the advantage having root exponential convergence. So this is very good because this allows us to get to the level of precision that we need without ever having to put a huge amount of basis functions or of collocation points. So as I said, this combines ideas of Fox, Henry C. and Moller, and then Betke and Trefethen, and Gopal and Trefethen, and Gerard and myself, and Joel and Bruno as well. Okay, so using this combination of ideas, also handling the holes, and so on, we are able to get these approximations for U2 tilde and lambda 1 tilde. So at the bottom, you can see the U's, the U tildes, and at the top, you see the lambda tildes. And you can see also, for example, lambda 1 tilde and U1 tilde, which was something for which we didn't need a lot of precision because it was very far from the rest of the spectrum. This is extremely quickly. We just need 17 coefficients and 51 collocation points. And this does the job. This gets a precision which is good enough to separate the eigenvalue from the rest of the spectrum. And on the other side, we have U2 and lambda 2, which require a lot of coefficient and a lot of collocation points, despite the root exponential convergence. So if it weren't for the root exponential convergence, then I don't think we would be able to get to this level of precision. And in the middle ground, there are lambda 3 and lambda 4 and U3 and U4, which are sort of halfway. Okay, so this is telling us that we have apparently 4 modulo this double eigenvalue, but we have 4 candidates to be our approximate eigenvalues and our approximate eigenfunctions. Okay, now what do we do with them? Well, we use the stability theorem by Moller and Payne, which essentially says that if your function is not 0, but it's equal to this number mu normalized with the area and some L2 norms on the boundary, then and I have a solution which is an eigenvalue for some lambda, but is not satisfying necessarily the boundary conditions, then I can find an eigenpair nearby. And I can get explicit estimates on how close the eigenpair, the true eigenpair from my approximate eigenpair is by means of this quantity here. So this is of order mu. And then I can also bound the L infinity norm of the approximate eigenpair by the L infinity norm of the minus the L infinity. Sorry, I can bound the L infinity norm of the difference between the approximate and the actual eigenpair by means of, again, the values at the boundary, and then some function that depends on the Green's function of the domain, which one can bound easily in this way. And more importantly, this number here, 1 over alpha, which measures the distance from the approximate eigenpair to the spectrum. Okay, so we have to control, and this is important and plays a role later on for the double eigenvalue, the distance between the approximate eigenpair to the rest of the spectrum. Okay, so this is good, and this is good enough for lambda 1 and lambda 2. Now, what about lambda 3 and lambda 4? Well, if we do that, then we get this value of mu for the parameters that I mentioned before, and we get these enclosures of lambda. Remember that since we don't have bounds on the distance to the spectrum, at least at this point, because these two, it's not clear how close they are from each other, then at this point we don't have bounds on the eigenfunction. Okay, so the enclosure of lambda is good enough so that we can split lambda 1 and lambda 2 from the rest, and we have some more to do regarding lambda 3 and lambda 4. Okay, so how to deal with the double eigenvalue? So for the double eigenvalue, we weren't interested on proving that it is a double eigenvalue, and what we did was what we needed, which was to prove that inside this this region here, there are actually two linearly independent eigenfunctions. Okay, so we're going to now show how to prove that within this bracket there are two linearly independent eigenfunctions close to this one and to this one. Okay, and the proof is going to go by contradiction. So it is enough, as I said, the problematic is that we don't have lower bounds for the distance to the spectrum, because a priori we don't know that these eigenfunctions correspond to the same eigenvalue, or they are just very close to each other. So the estimate for alpha, which is the distance to the spectrum, will blow up. Okay, so this is a problem, and it is enough to show that the true eigenfunctions are not proportional to each other. So that would save the day. So instead of doing that, then we're going to give up a little, and we're going to prove that there are two eigenvalues in a slightly bigger cluster. So in a slightly bigger interval, we're going to prove that there are two values, that there are two eigenvalues. Okay, and the proof is going to work by contradiction. So if we had one, then we would get a lower bound for the distance to the spectrum. And then we can get L-infinity estimates for the true eigenfunction. And now we can do that for these two and prove that indeed they are not proportional to each other. So then we have found two eigenfunctions where there was meant only to be one. So contradiction, and this is contradicting the fact that we are assuming that there is only one eigenvalue in this slightly bigger cluster. And this finishes the proof. This isolates the other two, and this finishes the proof for the double eigenvalue part. Now, how to finish the whole thing? So now we have our U2, which is close to our U2 tilde, with some explicit bound, L-infinity bound. And what we do now is we construct this curve gamma and prove that U2 is strictly negative on the whole gamma. So by symmetry, we only have to consider the color piece, but and then there we can prove that that U2 is actually negative everywhere. So this combined with the fact that U2 is positive somewhere inside the region enclosed by gamma shows that the nodal line is fully contained inside of gamma. And then because of Courant's nodal domain theorem, there cannot be other pieces of the nodal domain outside of this region. So then the only piece of the nodal domain is given by this sort of blue region, and it's contained inside gamma, and therefore it is closed because it doesn't intersect with the boundary, neither the boundary nor the holes. So this finishes the proof, and this finishes the theorem. And I'm going to stop here. Thanks a lot for your attention.
Thank you very much for this nice talk. We have time for questions, and so please, everyone, if you have a question, just unmute yourself and go ahead. Anyone?
I have a question. So how did you, for the second problem, meaning identify this domain as a counterexample, meaning possible?
You mean in the at the non-rigorous part, at the non-rigorous level, or at the rigorous?
Yes, at the non-rigorous level. I mean, you need to guess. Yes.
We did many experiments trying with different sizes and different holes and different positions. This is how we also could identify all the other funny domains. So we tried many, and then and then all of these seemed to work in the sense that the nodal line was closed. But when it came to proving the actual estimates, then there were domains which were better than others, and in particular, this last one was better. So here there is a compromise between the gap between the second and the third, and also the distance that you have to beat in order to enclose the nodal line. So these two things sort of push against each other. If you can get a domain that has a big gap, then it's very flat, and and you have to, the distance that you have to beat is very small. So the last one has some kind of compromise between these two quantities that seem to push against each other. But to answer your question, we did a lot of experiments and we tried many domains, and we ended up with this as candidates. But we sort of ran an extensive search of possible shapes of the holes, which we were trying to keep with a minimum amount of sides, and possible locations and widths. And this is what we got.
Yeah, I mean, why hexagonal? Why the hexagonal domain? And
because if you try with less sides, then
yes,
the less sides that you put, it is more challenging, because then the nodal line is not going to be close. If you try with something that sort of look like this, and say you put some holes here, then the nodal line is going to look like this, and it will touch. So then if you sort of put few holes, then it is more likely that the nodal line is going to touch the boundary of these holes.
Thank you very much. Thank you.
Question and answer. There is a question in the chat from Corentin. He's asking, is there hope to treat the original counterexample in the same way, with the astronomous number of holes, I guess?
What do you mean in the same way? Like constructing a guess and then proving that close to the guess there is a true solution nearby. This is somehow inheriting a little bit of that philosophy, in the sense that, okay, we played with the diameter and with the location of the holes, but sort of we put some holes kind of in the middle of a roundish shaped domain. So in some sense, it also is following that sort of philosophy. It's just that we did it with few holes. If you want to do it with more holes, you probably can, but then it depends a little bit on the position and on the size of the holes. If you make the holes very small, then you may have problems, and if you have many holes, then you may also have problems as well. But in this case, we're sort of trying to go the other way around. We're trying to get few holes, not many.
So I'll go ahead, Corentin.
No. My question was, in this original counterexample, is it possible to do it with few holes?
Oh, they don't know, and I don't know either if you can make the estimates quantitative. At least from the remarks of the papers, it seemed difficult, but I haven't tried very hard to try to make the estimates quantitative in that sense. But at least from the remarks of the people who wrote the papers, this seems difficult.
But did you try to run the numerical experiment on the examples from the paper?
Yeah, it does work. Yeah. So this is sort of a starting point, and then if you tweak a little bit the holes, then it is somewhat stable. So yeah, that's sort of the very first example that we tested was, okay, let's take the one for the paper, do 50 holes, make sure that it works, and it does work. And then let's try to keep removing holes. So yeah, of course.
How important is it that your domain is symmetric?
It is important for technical reasons, because when it comes to constructing the solutions, we use the symmetry heavily in order to minimize the amount of functions that we put, in order to make the systems that we have to solve, in this case, 6 times smaller. If we consider asymmetric domains, then our systems would be 6 times as big. And then this is sort of already in the danger zone for hardware. So we try to use this to our advantage. But that's the only reason. If you perturb it a little bit, then it's probably going to work as well.
The fact that you have these double and almost triple eigenvalues is, one could think that it's linked with the symmetry, right?
Yeah, definitely. If you look at the eigenfunctions, yeah, you can see this is sort of very clear here that this is coming from the symmetry. Yeah.
There is a comment in the chat by Lotfi Hermi. He's saying just a remark on the discretizations on some of the inequalities. You can find them in the work of Bramble and even Weinberger as early as 1951.
Okay, I didn't know this, and we'll take a look at this. Thanks a lot for the comment.
Yeah, thank you. Is there any other comments, questions from anyone?
This is Dorian. Maybe I have a short question. So if you want to certify your numerical computations for eigenvalues and eigenfunctions, do you suggest that it is always better to use particular solutions rather than finite elements?
No, always is a very strong word.
I mean, for polygons, let's say.
So far, this has been better for us. Maybe there is an instance where the finite elements works best. It may depend on the index heavily as well. So depending on whether you're trying to certify a low index or a high index. I mean, in our experience, it has worked better to do this in these two passes. I make no claim that this is always going to be the case, but we've tried both. And the point is that if one does the finite elements, which is good because it gives you the index, then this is usually not good enough for managing to bridge the gap and so on. And if you do particular solutions, then you have the problem that you don't know the index. So there are advantages and disadvantages to both, and we try to patch them together. Maybe you can get away if you have monotonicity arguments, for example, depending on the type of problem that you're doing. Maybe you can get away to use some sort of arguments like that to get good lower bounds. Here the problem are the lower bounds, of course. So if there is a trick, depending on the domain, or you can use some homotopy or something like that, then maybe that could work. But so I guess the answer is depends.
Okay.
But in these cases, it sort of worked better for us the way we did it.
Okay, thank you.
I have a question. When you were looking for candidates at the non-rigorous level, did you find candidates that had less holes than this one?
No.
Okay.
But very close. So probably we can dig in a little bit more, and maybe we weren't perturbing in the right way. I think 4 can be done. 4 holes.
Yeah. Thank you.
But we didn't manage to, or it was sometimes it was not very clear because then you're sort of at the level of the finite elements or whatever you're doing at the non-rigorous level, sort of reaching the point where it is unclear whether it is 0 or not. So if it wasn't there, it was close. But yeah, possibly 4 can be done.
Anyone else wants to ask something or comment on something? If not, let's thank Javier again. Thank you very much. And let me just mention that we will next week have a talk by Paolo Luzzini, who will speak on asymptotics for the buckling problem. Until then, I wish you all a very good week, and thank you very much again for the talk.
Thank you.
Bye-bye, everyone.